Welcome back everyone to this lecture where we're going to be discussing performance evaluation. And specifically, we will be discussing regression metrics. So now that we have a fitted model of scikit-learn that can perform predictions based off of features, how do we actually decide if those predictions are any good? Fortunately, we have the known test labels to compare our results to. So let's take a moment now to discuss evaluating regression models. And we're not just talking about linear regression, but just a regression task. And recall, a regression is a task when a model attempts to predict continuous values, unlike categorical values, which is a classification task. So for example, attempting to predict the price of a house given its feature set is a regression task. Attempting to predict the country a house is in, given its features, would be a classification task, since there's no true in-between values for two separate countries. Now, you may have heard of some evaluation metrics like accuracy or recall. However, these sort of metrics aren't useful for regression problems. We're not going to be able to say how accurate our model is in terms of accuracy. What we need are metrics designed for continuous values. So now let's take time to discuss some of the most common evaluation metrics for regression. And those are mean absolute error, mean squared error, and root mean square error. And we're going to start with the simplest, mean absolute error, and then slowly build up to root mean square error. Keep in mind again, the metrics shown here apply to any regression task, not just linear regression. Later on, if we were to apply a random forest regression algorithm, we would be using the exact same metrics discussed here. Okay, let's begin with mean absolute error. This is the mean of the absolute value of the errors, and it's pretty much the easiest error metric to understand. All we're doing here is we're going to directly compare the error between our prediction and the true value. So we have the formula, and if we start over on the right-hand side, I can see that for every row I in my predictions, what I'm going to do is grab the true y-test value of y of I and subtract my prediction from it, which is y hat. And since my predictions could be technically above or below the true value, in order to make sure that I don't average this out so that it's 0, I'm just going to take the absolute error. Just from an absolute factor, how far off are my actual predictions? And then we're just going to take the average across all the predicted rows. So again, it's just the y-test label, subtract our prediction from it, take the absolute value to get your error in terms of absolute value, and then you sum them all up for n number of prediction rows and divide by total count n, which is why we have a 1 over n outside of that sum. Now what's the issue with mean absolute error? Unfortunately, it's not going to punish when you're really off for just a few points. Recall the Anscombe's quartet here is showing us the same regression fit line for a variety of data points. And if we take a look at the specific example on the lower left, notice here that if we were just to take a mean absolute error of this regression line, for the majority of the points, we are actually doing a pretty good fit. However, we have one point that is extremely far off. And if we just use mean absolute error, we're not actually going to be aware if we are really off for just a few points. And we want our error metrics to account for these. We want some sort of reporting metric that does take into account if you're extremely off, even for just a few points. So how could we actually fix our error metric to try to account for the case where we maybe really have large errors for just a few points? To fix for this, what we could do is use a mean squared error. And here, larger errors are quote unquote punished more than with mean absolute error. And essentially what we're doing here is instead of taking the absolute value of that difference between our prediction versus the true y-test value, what we're going to do is square it. And when you square it, you're going to really punish your model that if it has a large error, even for just a few points, squaring it is really going to increase the overall effect on the average of those few points that are really far off. Now there is an issue with mean squared error, and fundamentally the issue is that it's actually reporting back your error in different units than your original y value. So what it's actually reporting are units of y squared. If we think back to the example of predicting the price of a house, mean absolute error would report back your error in terms of dollars. It would say, on average, you're off by X amount of dollars. Here, if we were to report back mean squared error, we would actually be reporting back how far you're off in squared dollars. And that's really hard to interpret. You can't really go to your boss and say, oh, my error is 100,000 squared dollars, because that's very difficult to understand what your actual true error term is. So what we could do is to fix this issue and get it back into units of the original y, we'll simply take the square root of everything after we're done. And this is known as root mean squared error. And it's really analogous to a standard deviation instead of reporting back variance. And this is one of the most popular metrics because it's going to punish those larger errors by squaring them. And it also fixes the issue of the squared units of y by taking the square root, since this is reporting back your error in the same units as your original y value. And it's punishing those larger values. So the most common question we get from students at this point is, what is a good value for root mean squared error, or really any error metric? And the issue is, context for answering this question is everything. A root mean squared error of $10 is really fantastic if you're trying to predict the price of a house, which is usually in terms of something like hundreds of thousands or even millions of dollars. But if you're trying to predict the price of a candy bar and your root mean squared error was $10, that's a horrible error because you're way outside the range of typical candy bars. So again, the context of what your average value is for your label helps you understand the answer to the question of what is a good and acceptable value for your error metric. You should also be comparing your error metric to the average value of the label in your dataset to try to get an intuition of its overall performance. And this is also where domain knowledge plays an important role. Keep in mind that context of importance as well as historical models is also necessary to consider. We may be trying to create a model to predict how much medication to give, in which case even a small fluctuation in root mean squared error may actually be very significant. Or if you're thinking about creating a new model to try to beat historical performance, like creating a model to try to improve on existing human performance, what you need is some sort of baseline root mean squared error to compare to. It's highly likely that someone else has already tried to solve the same regression task that you're trying to solve, and in that case, you're going to want to compare your root mean squared error not just in absolute terms to your particular work, but also you want to compare it to prior work and make sure you're actually improving on previous work that's been done. Let's quickly jump back to the notebook that we were just working with in the previous lecture and calculate these metrics with scikit-learn. All right, here we are at the Jupyter notebook. Recall in the previous lecture, we created our linear regression model and then we fit it to only the training data. And now that we have a fitted model, what I can do is simply say model.predict, and I can pass in a set of X features and then predict what the appropriate sales amount will be. So what are the features? Well, we know from the original data set when we define X, the features are simply my advertising spend on TV, radio, and newspaper. So how can I actually fairly evaluate the model? What I want to do is evaluate it on data it's never seen before. In this case, I know that it's never seen X test. These are features that it was not trained on. So what I want to do is predict off of X test and compare its predictions to what I know are the correct values for X test, which is Y test. In fact, let's go ahead and comment out all of this and just see, what does X test look like? If you take a look at the head of the X test data frame, it looks something like this: values for TV, radio, and newspaper spend. And then, due to the random shuffling, I can see the appropriate index. So 37, 109, 31. If I take a look at Y-test, again, it's the corresponding true sales value for each of these advertising spend ranges. So it starts off with index 37, matches up here. So for this particular combination of TV, radio, and newspaper advertising spend, in my historical data, I know I was able to achieve 14.7 either units of sales or dollar amount in sales, whatever the unit happens to be. Then I know for this particular combination at index 109, I achieved 19.8, and then 31, and so on. So what I'm going to do is use the model to predict for each of these rows and then compare those predictions to my Y-test. And luckily for us, that's super easy to do for scikit-learn. So simply, we just go ahead and uncomment this. and I'm going to say here that model.predict off that set of X test features, and then we're going to say this is my, well, let's say test predictions, since I'm predicting off the test set. So we run that, and then my test predictions, if we take a look, is just an array of predicted values. So how do I actually compare test predictions to y-test? Well, we just learned that there are three main ways of doing that: mean absolute error, mean squared error, and root mean squared error. And luckily for us, scikit-learn comes with built-in functions for these. I simply say from sklearn.metrics import, and then it's mean absolute error, and then mean squared error. And for the root mean squared error, I can simply take the square root of mean squared error. Okay, so let's start off with mean absolute error. Recall that that's going to just say, on average, I'm off by this amount. So if I take a look at the sales from the original data frame, what is the average sales value? Well, it looks to be about 14, either 14 units or $14,000, whatever the units of sales happens to be, but the average value is 14. I can also check out a histogram by saying histplot and saying data is equal to df and x is equal to sales. And this will also report back the general distribution of the sales. So it looks like they range from somewhere to like 0 to a little over 25. Of course, I could increase the bins to try to get a little more clarity on the general distribution. But overall, I can see the general range for my sales values. And I'm going to be able to directly compare this to my mean absolute error, since they are in the exact same units. So how can I do that? For mean absolute error, I simply say mean absolute error, and it's going to take in your true y values, that's y-test, and then your predicted values for y, which are test predictions. So I say y-test, and then I'm going to say test predictions. And if you run this, it reports back your mean absolute error. So the obvious question is this a good mean absolute error value? Of course, context is everything. Did I already have a historical model that tried to predict sales based off features? If so, I should be comparing my current mean absolute error to that historical model. Or if I've never actually created a model for this, how can I judge this in terms of just my data? Well, I should be comparing it to overall the average sales value as well as the distribution of sales values. Here I can see that my average sales value is about 14, and I can see the distribution kind of goes from 5 to 25. And then my mean absolute error, basically on average, I'm off by, and it looks like I'm off by 1.21. Is that good or bad when compared to 14? Well, it's a little bit than, let's say, a 10% error range. So is 10% error acceptable? Again, it kind of depends on the context of the situation. But at least now I have an understanding based off the data of my model's true performance on data it's never seen before. So on data that the model has never seen before, on average, it's going to be off by 1.21, which if I compare it to my average sales values, is a little less than 10%. Okay, so that's mean absolute error, but this again doesn't take into account situations where my model could be really far off for just a few points. For that, I'm going to want mean squared error and then root mean squared error. Luckily, it's pretty much the exact same thing. I simply call mean squared error and then pass in y-test and then test predictions. And now my mean squared error, again, that's going to punish values that I'm really off for, is 2.298. This value, however, I cannot directly compare to the mean because this is now in squared terms of y. To fix that and get that for root mean squared error, I can simply say np.sqrt, and this will take the square root of this mean squared error, which reports back the root mean squared error. So this right here is the calculation for root mean squared error, and it's 1.51. The analogy for this is basically the standard deviation of your predictions, and mean squared error could be thought of the variance for your predictions. And it looks like it's also more or less pretty good. It's hovering kind of around that 10% range. So what I like to do is kind of use both mean absolute error to make sure on average I'm doing pretty good, and also root mean squared error to make sure I'm not super far off for just a few data points. If you got a mean absolute error that was performing okay, but you got a really horrible root mean squared error, then that's basically informing you that your model's performing pretty well for most points, but you have a few data points where you're way off, and that is going to show up when you're squaring that error. Okay, so again, take a look at the lecture notebook. We kind of explain how each of these is interpreted as well as calculated. And what we're going to do is in the next lecture, we're going to take a deeper dive into residuals themselves. And that will help us understand whether or not linear regression was a valid model choice. I'll see you at the next lecture.